want returned. A mechanical rake system is used to keep the bar screen clean. This chain, which operates the rake mechanism, helps filter out the trash, separating it away from the wastewater. The rake dumps the solids into a bin inside the station, manually cleaned out, and is later hauled to the landfill. Take a look at the bottom of this rake mechanism. Over 45 years of wear and tear has caused the bottom supports to rust through. Staff had to re-engineer and fabricate a piece of 1.5-inch channel iron to replace the existing support to keep the mechanism operational. Purchasing replacement parts for this equipment is not an option. It's too outdated. Examples like this show just how valuable it is to have a skilled staff in place to address a variety of fabrication challenges. Part of the wastewater treatment plant's capital improvement plan is a project to construct a new bar screen and rake mechanism. Rather than manually having to clean the mechanism as they do today, an upgrade would automatically shred, compact, and wash the waste, drying it into a very fine material which would then be hauled to the landfill. Over the next 2 years, the facility is aiming to become a cleaner operation by installing a much finer screen into this part of the process, which in turn will filter out more waste and reduce wear and tear on the pumps at the plant. Wastewater continues through the bar screen and into the wet well, where grease balls begin to form. Simply put, grease that is dumped down the drains and empties into the sewer system will form a ball around any solid waste item in which it comes into contact. An example would be grease forming around a cigarette butt or dish rag. As it forms, these grease balls can become larger and larger and eventually have to be cleaned, which requires staff to collect the grease balls every few weeks. If they are allowed to get too big, they have been known to plug pumps and cause a variety of damage. You can never tell by looking here, but wastewater is actually 99.8% water and less than 0.2% solid material. Once the wastewater enters the facility, we dive a little deeper, if you will, into the pump station wet well. We are now down 15 feet below grade, or below the ground. The sewer, which brings all the wastewater in, is closer to 25 feet below grade, or below the ground, which means there is 10 feet of raw sewage under our feet at this point, 5 feet of open air, and another 10 feet of raw sewage. The pumps on the other side of this wall pick up the sewage and take it to what is known as the headworks part of the facility. There are 18 sewage pumps which pump raw sewage out of the city and into the wastewater treatment plant. The raw wastewater pumping station at the plant is the largest lift station in the city of Grand Island. It consists of 5 main pumps with a capacity to pump up to 40 million gallons of wastewater a day. The ability to continue to pump wastewater every day is critical. That's why this settle and are removed. This facility will pull out up to 2 cubic yards of grit per week, almost enough to fill a normal-sized pickup. Heavy rain events can double the grit because of I&I. Next in the process, wastewater moves to the primary clarifiers. The primary clarifiers are speeding up the process of Mother Nature by allowing solids to settle out. If raw sewage was dumped into the environment, be it in a lake or river, the first part of the process that would take place is the settling out of solids, exactly what we see happening here with the primary clarifiers. The primary clarifiers are a 75-foot diameter tank with a sloping bottom where primary settling occurs. The outside depth of the tank is 7.5 feet, while the center depth of the tank is 10.5 feet. To promote settling, the flow of wastewater is slowed through the tank, taking from 60 to 90 minutes to flow through. The primary clarifier mechanisms were replaced in 2010. The skimmers you see going around the tanks are only a very small part of that mechanism. Down below is a very large steel framework that moves around the tank. At the bottom of the mechanisms are scrapers that work with the slope bottom and move the solids to the center of the tank for removal. The solids are pumped off using a progressive cavity pump to a holding tank where they are kept fresh by adding air. The water that comes off the primary clarifiers has 25 to 50% of the suspended solids removed. So we began the process with the flush. It carried through the city mains, across the bar screens, through the wet well, into the main pumps, past the grit basins, and out of the primary clarifiers. We have now completed the primary treatment process and are now ready to move on to the secondary treatment process. An interesting side note, on a typical day the facility will remove 10 to 15 tons of suspended solids and BOD, biochemical oxygen. Each basin contains approximately 2,500 ceramic diffusers to break up the air into little tiny bubbles so that the biological life can use the oxygen. The first part of each aeration basin is 700,000 gallons and operates as an anoxic zone or without oxygen. The second part of each basin is 2 million gallons and is aerated or oxic, meaning with oxygen. Once ammonia nitrogen hits the aerated part of the basin, it converts into nitrates by uptake with the oxygen. This is when the 400% recycling begins its process, this time landing in the anoxic zone, allowing the bugs to take the oxygen molecule off of the nitrates, leaving nitrogen gas behind. So in general, we nitrify in the anoxic zone and denitrify in the oxic zone. What we are looking at now is the bacterial flock as it mixes in the anoxic zone. It's attempting to coagulate or stick together. Without the giant mixers that are in these basins, the water would turn clear on top and all of the solids would settle to the bottom. This would not allow the bugs to make contact with the nitrates, thus not uptaking the oxygen off the nitrate molecule, and the nitrify and denitrify action wouldn't happen. While we have said that we are accelerating the process of Mother Nature, it's interesting to note that through the recycling process, solids remain in the system up to 16 days. There are several hundred tons of solids within this system, with only 2 to 3 tons being removed each day. Without the solids containing the bugs, there would be no way to treat the waste. It's ironic that removing the solids is the focus treatment in the beginning, only to be added back into the treatment process later to further treat the water by supplying food for the bugs. Who would have thought that removing the solids from the water is as vital as adding them back in? Once the water leaves the aeration basins, it goes back to clarifier basins, but this time they are final clarifiers. A fence surrounds each of the 3 clarifiers to prevent excessive wind loading on the surface. On a windy day, scum buildup will get pushed to one side and go over the edge, releasing solids with the final effluent, or water going out of the plant. The final clarifiers act very much in the same way as the primary clarifiers, with the only real difference being the depth. The deeper clarifiers allow more solids to settle out. These upright pumps are what move the solids from the final clarifiers back out to the aeration basins for recycling. Each one is capable of pumping 3 million gallons per day. The smaller pumps on the left are used to waste the solids out of the bottom of the clarifier and back to the waste sludge holding tanks we referred to earlier. Each of these recirculatory pumps has a price tag of over $20,000 apiece. According to the NDEQ, or Nebraska Department of Environmental Quality, the Wood River is classified as a warm water B stream, which means the effluent must meet warm water B stream standards for fecal coliform and E. coli. A UV disinfection facility disinfects the water as a part of the treatment process. UV is considered to be a very safe and efficient means of wastewater disinfection. Inside of the UV disinfection facility, we elevated a bank of UV lamps to help illustrate not only what is being used in this part of the process, but how they work day to day. The small circular white rings that are moving back and forth are actually cleaning the lamps. Each ring contains a scraper to clean the bulb. The center of the ring contains a lime-away gel to remove hard water stains off of the bulbs. The cleaning mechanism is powered by the hydraulic system seen here. The fluid used within this system is a food grade, which means if a leak were to occur, the employees and the environment are not harmed. There is quality control sampling and testing performed throughout the plant, but here at the final sampler is the most important sampling that is performed. This sampler takes a portion of the plant effluent, or water going out, with 2 to 4 samples every hour. Facility staff also test every day for BOD, suspended solids, nitrogen, and E. coli. Test results determine whether or not the plant is protecting the environment and meeting the permit requirements. This facility supports 240 feet of finger weir within the UV disinfection system. Under the grate, you can see the small channels that are a part of that system. A weir is an engineered system used to maintain a constant flow of water. It's in place to ensure that the flow of water being treated is not coming through the system too fast. In other words, every drop of water is receiving the same amount of exposure to the disinfection system to ensure permit requirements are being met. The flow that exits the UV disinfection system here on the northeast side of the building travels down through this junction box and out through this discharge, which contains again a partial flume. It continues down another junction box and out a 42-inch pipe into the storm sewer outfall ditch that is north of Swift Road. After all the treatment, this is what is left behind. At this point, the water is less than 10 milligrams per liter suspended solids